In this video, I want to motivate and illustrate the Ford-Fulkerson algorithm for the max flow problem. In a max flow problem, we are given a directed graph with edge capacities, and we are trying to find the maximum possible flow from a given source vertex to sink vertex. As a motivating example, we can think of the edges in the graph as representing pipes. And so what we are trying to calculate is how much water could flow through the pipes from the source to the sink. But part of the reason we're studying max flow is that there are lots of other problems that we could formulate in this way, including traffic flow on the roads of a city or data flow on a computer network. But another reason to study max flow is that it gives us a good first example of a constrained optimization problem, and constrained optimization comes up in all sorts of contexts in math and computer science. And also, we study max flow because it turns out that there are lots of other problems that can be transformed into max flow problems. And so if we have an algorithm for max flow, then we can solve those other problems by reduction. So in our formal description of the problem, we are given as input a directed graph, and for every edge in the graph, some integer capacity. We're also told which vertex is the source and which vertex is the sink, and our goal is to find the flow from the source to the sink with the maximum possible value. To understand this output that we're looking for, we should formally define a flow. Intuitively, a flow corresponds to some amount of water that we are sending from S to T, and the maximum flow would be the most water we could send without exceeding the capacity of any pipe. But we define this formally by calling a flow some function that tells us the amount that is traveling on every edge of the graph. So the flow function maps edges to non-negative integers, telling us how much flow is on that particular edge. And that flow function must meet certain constraints. First is the capacity constraint, that the amount of flow on any given edge must be no less than 0 and no more than the capacity of that edge. And second, we have capacity constraints saying that no flow magically appears or disappears. We represent that mathematically by saying that for every vertex, the total amount of flow coming into the vertex has to be equal to the total amount of flow going out of the vertex, unless that vertex is the source, which can have more flow coming out, or the sink that can have more flow coming in. We define the flow in to a vertex to be the sum over all of the edges coming into that vertex of the flow on those edges, and likewise the flow out from a vertex is the sum of the flow on all of its outgoing edges. And so the capacity constraint says that flow in and flow out are equal unless we're talking about the source or sink. Now that we've formally defined a flow, we can call the value of any given flow function the amount of flow coming out from the source, or the amount of flow going into the sink. We can define this value either way because they turn out to be equivalent. The conservation constraints ensure that for every vertex that isn't the source or sink, their inflow is equal to their outflow. So if we have some amount of flow coming out of the source, that flow must go somewhere, and it can't terminate at any of the vertices other than the sink, because then they would have an imbalance. And so whatever flow comes out of the source must go into the sink, and so these two must be equal, and we can use either of them to define the total amount of flow from the source to the sink. Given all of this, our output for the max flow problem is a valid flow with the maximum possible value. So, how can we compute the maximum flow for a given instance? Well, we might first consider the greedy algorithm that I've outlined here. Our first step is to find a path from the source to the sink, and we can do that using any of our graph traversal algorithms. And then we want to push as much flow as possible along that path. Pushing as much flow as possible means figuring out what is the bottleneck edge on the path. For example, if we identified the bottom path from S to B to E to G to T, the bottleneck is the edge on that path with the lowest remaining capacity. Given the current capacities, that bottleneck is 2 from this edge. We could then push 2 units of flow along this path and update the graph to indicate the remaining capacities. So these 2 edges would only have capacity 5 remaining. This edge would be used up entirely, and this edge would have a remaining capacity of 1. Once we've updated the graph, we can repeat, finding some other path from S to T, and continue as long as there are any paths remaining from S to T in the graph. So now we need to think about whether this greedy algorithm is correct. First of all, does it find a valid flow? Can we argue that it produces a flow function that respects the capacity and conservation constraints? And if it does give us a valid flow, is that flow always going to be maximal? I encourage you to pause the video here and think about this yourself. And to build some intuition, I'm going to try carrying out our greedy algorithm on this max flow graph. By inspection, we can tell that the maximum flow of this graph should be 3. We could send 2 units along the bottom route and 1 unit along the top route. But as we execute our algorithm, we will be finding some path from the source to the sink on every step, and so we should consider the possibility that the first path we find is this one. In the case that we identify this path first and push as much flow as possible, we will find a bottleneck of 2 from either of these edges, and so we will push a flow of 2, which we can record in a tabular representation of the flow function. And now we can update the graph to indicate the remaining capacity of each edge. And when we go back to the top and try to find a path from S to T, our graph traversal gets stuck because there is no S to T path, at which point we conclude that this must be a maximum flow. But clearly that's wrong, because we saw before that our starting graph could have had a max flow of 3. So what went wrong here? Well, the core issue was that we chose an inefficient path. As it turned out, this first path that we chose wasn't making the best use of the available capacity, so we need to come up with a way to either ensure that we pick good paths, or to allow ourselves to go back on our choices if we happen to pick a bad path. In this case, it might have been obvious to you that the path I was choosing was a strange one, but in even slightly more complicated graphs, it's hard to know right away whether a path that we are choosing is going to contribute to the best possible solution or not. And so, instead of trying to always pick good paths, I want to focus on allowing ourselves to undo some of our decisions if they don't work out. And the way we'll do that is by keeping track of a residual graph. The idea of the residual graph is that we want to incorporate information about the flow into our graph data structure in such a way that when we look for paths, we can identify as part of the path potentially undoing bad flow decisions that we made earlier. And what that looks like in practice is to add a back edge for every directed edge in the graph, where the capacity of the back edge is equal to the flow on the forward edge. When we begin, our residual graph corresponds to the original graph for the problem, with back edges added that have initial capacity 0. Then when we search for paths, we will be searching in the residual graph, but we will ignore any edges with capacity 0. And that means at the start, we're searching in exactly the same graph we were before. So if we find this same initial path and update the flow, we'll now perform our graph update step on the residual graph. And when we update the residual graph, every time we deduct from one edge, we want to add the same amount to the reverse edge. So we subtract 2 from SA and we add 2 to AS. We do likewise for the other edges in our path. And now, when we return to the top and look for another ST path, this time we will find one. Ignoring the 0 capacity edges means we still can't go from S to A, but we can now use the back edges in the residual graph and find the path S to B to A to T. The minimum capacity on that path is 1, so we will push 1 unit of flow. For the edges S to B and A to T, that looks exactly like what we just did. We'll add 1 to their flow, subtract 1 from their capacity, and add 1 to their residual capacity. On the other hand, for the edge B to A, since that was not an edge in our original graph, but rather one of the back edges we added for the residual graph, we will still change the capacities by 1, lowering the capacity on the edge we're using, and increasing the capacity on the edge that goes the other direction. But what this means in terms of the flow is that we have reduced the amount of flow going from A to B. So in our flow table, we need to reduce the output on the AB edge to 1. Now we should check that the resulting flow still meets our capacity and conservation constraints. I'll restore this graph to show the original edge capacities. For each edge, we should check that its flow is less than or equal to its capacity. SA has capacity 2 and flow 2. For SB, 1 is less than or equal to 3, 1 is less than 3, 1 is equal to 1, and 2 is equal to 2. So all of our capacity constraints are respected, and we should check that the total flow coming into each vertex is equal to the total flow coming out, except at the source and the sink. For A, we have a total of 2 coming in and 2 1s coming out, And at B, we have 2 1s coming in and 2 coming out, meaning the in and out flows are balanced, which means that our conservation constraints are respected, and the total outflow of S is 3, which is equal to the total inflow of T, so the value of this flow is 3, which beats out our value 2 flow from before and matches what we said was the best we could do. So let's modify our algorithm outline to incorporate our residual graph. So before we begin, we have to initialize the residual graph by adding the back edges with capacity 0. Then when we are searching for paths, we will search in the residual graph and we will ignore any edges that have a weight of 0. When we update the graph, we will be updating the residual graph where every time we subtract from one edge, we add to its reverse edge, and we no longer delete edges. We can keep around edges with capacity 0 as long as we ignore them in our pathfinding. And finally, when we are pushing flow along a path that we have found, we add flow to edges that were part of the original graph, but if we have an edge that is only present in the residual graph, not our original input, then we should reduce the amount of flow, because having that edge as a part of our graph means that we want to undo some flow that we already pushed. To understand what we mean by undoing flow that we pushed, it's worth thinking for a moment longer about what happened when we identified the path that used a residual edge. Originally, we found a path that used the edge from A to B and pushed 2 units of flow along it. But our eventual solution only pushed 1 unit of flow along that edge. So when we identified our second path that used the edge from B to A and reduced the flow on this edge, what that was saying is that we had flow coming out of B of 2 units, and rather than having all of that flow come from A, we could instead have part of that flow arrive along this path. So B can still have an outflow of 2 when we reduce its inflow here by 1 and increase its inflow here by 1. Similarly, before we found this second path, the flow coming into and out of A was 2 units, and all of it was going to B. But now we've rebalanced the 2 units of flow coming into A to instead have just 1 unit going to B, and now 1 unit is going on the A to T edge. So our path included the A to T edge, meaning we were adding flow to that edge, but when we subtracted flow from the A to B edge, we were saying redirect the flow that was previously coming into A and going out through B to instead go out towards T. So one way to think of what's happening when we find a path that uses a residual edge is we are finding some other way of getting B the flow that it needs, and some other way of using the flow that A is already receiving, because we've found a more productive use than sending flow from A to B. One complication that doesn't show up in our first example of a residual graph, but can show up in general, is when the graph that we start with already has edges in both directions. In that case, we don't need to add back edges, but we need to be a little bit more careful about how the flow relates to the edges in both directions. So we will formally define our residual graph in a way that takes this into account. So we define the residual graph in terms of the graph and the flow. So for any given flow, we will have a different state of the residual graph. And for all edges in the original graph, we have both the edge and the back edge in the residual. And the weight of an edge in the residual graph is the original capacity of the edge minus any flow that is currently on that edge plus any flow that is currently on the reverse edge. In the case of an edge that is not present in the original graph, it will have no capacity and no flow, so its weight will just be the flow on the edge in the other direction. For edges that are present in the original graph, but don't have a reverse edge in the original, they will never have a flow in the other direction, so their weight in the residual graph is their capacity minus their flow. But if we have vertices in the original graph that have edges in both directions, then if there is flow on one of those edges, that will affect the residual weight of both. For example, a flow of 1 from D to E would subtract 1 from the weight of DE and add 1 to the weight of ED, so we would have residual weights of 1 and 2. In that example, if we later route flow from E to D, we will first lower the usage of the DE edge before we start pushing flow in the other direction. So we've now outlined the Ford-Fulkerson algorithm for solving max flow. Next, I'd like to trace through the execution of Ford-Fulkerson on this example graph. But if you already feel confident in how the algorithm works, feel free to skip ahead to this timestamp when we will start sketching the argument for its correctness. Our first step is to construct the residual graph, so we need to add back edges everywhere we don't have one. And since there is no flow so far, all of those new edges will have weight 0, and we won't change the weight of any of the existing edges. Our next step is to identify a path from source to sink, and let's suppose the first path we found was SADFT. Along this path, the bottleneck edge is D to F, so we can only push 1 unit of flow, and we now add 1 to the flow for each of these edges. We now need to update our residual graph to correspond to our new flow values. I'll begin by decrementing capacity on the forward edges. And then we need to add capacity to all of the back edges. We've finished updating our graph, so we go back to searching for an ST path. Let's suppose the next path we find is S to A to D to C to F to T. And along this path, our minimum capacity is 1 from a couple of different edges. So we'll push 1 unit of flow. And increment the flow table accordingly. And now we have to increase the flow on the back edges. Now we look for another path. Suppose we find SBEGT. Along this path, our bottleneck is 2, so we will push 2 units of flow and update our function table accordingly. And now we have to reduce the forward capacities and increase the backward capacities. And now we search for another ST path. Let's suppose we find S to A to D to T. We have a bottleneck of 1, so we will push 1 unit of flow and update our function table. Then we reduce our forward capacities and increase our backward capacities. Now when we search for S to T paths, we might go from S to B to E to D to G to T. This path has a bottleneck of 1 in several places, so we'll push 1 unit of flow. And we update the forward and backward capacities. And at this point, if we weren't using the residual graph, we would be stuck, because we've used up the capacity of 2 of the 3 edges coming into T, and we've used up our capacity for getting flow into F, except via a path that uses residual edges. When we search for a path from S to T now, we'll find S to B to D to A, C, F, T. And along this path, our bottleneck is 2, so we will push 2 units of flow. When we get to the edge from D to A, that doesn't appear in our function table, which means we're operating on a residual edge. So what we want to do is reduce the flow on the A to D edge. So now, instead of sending 3 flow in this direction, we're only sending 1. And instead, we are redirecting the flow that was coming into A along the rest of this path. Now we need to update the residual graph. At this point, we truly are stuck because there's only one edge coming into T that has non-zero capacity, and there are no edges with non-zero capacity coming into F, which means that there is no way to find any path from S to T using only positive weight edges. So at this point, we declare our job done and return the flow that we have computed. The value of this flow is equal to either the total outflow from S or the total inflow to T. S has a total outflow of 3 plus 5, and T has a total inflow of 1 plus 4 plus 3. So either way, the value of our flow is 8. Now that we've seen Ford-Fulkerson in action, we should think about why is this algorithm correct? Now that we have a full tabular representation of a flow for this graph, we can note that for most of the edges, we can read off their flow from the residual graph by just looking at the weight of the back edge. On the back edge from B to S, we have a weight of 5, which is equal to our flow on the edge SB, and that's because we used up 5 units of capacity routing flow from S to B, and added back that same capacity in the other direction on the residual edge. This holds true for all of the edges that were new in the residual graph. the amount of flow that's going from E to G is equal to the weight of the residual edge GE. The only case where we have to be careful about reading off flows from the residual graph is where we had edges in both directions originally. Here, the flow is equal to the difference between the back edge's capacity and its original capacity. So our flow from D to C is 1 because we have one more weight on the CD edge than the original graph had capacity. Another thing to note is that every time we updated weights, we subtracted the same amount from the forward edge that we added to the backward edge, which means that for any pair of edges between the same two vertices, the total capacity of those two edges is always constant. Whenever we subtract capacity from one of the two, we are adding the same amount to the other. So I challenge you to now use these facts to help in proving the correctness of Ford-Fulkerson. Step 1 should be to argue that the flow we get from running Ford-Fulkerson is always valid by respecting the capacity and conservation constraints. To argue that Ford-Fulkerson gives us a valid flow, we should think inductively about every step where we push flow along some path, and demonstrate that that operation always preserves the conservation constraint that for every vertex other than the source and the sink, the inflow and outflow are balanced, and that this operation preserves the capacity constraint, always keeping the flow on any edge between 0 and its capacity. So if those constraints were true of the starting graph, and each push operation preserves them, then we will have a valid flow when we're done. And then it remains to show that the flow that Ford-Fulkerson returns has the maximum possible value of any valid flow in the graph. So for now, I will leave you with the question of how do we know this flow is maximal, and the hint that you should be thinking about cuts in the graph.